So yesterday we started our study of Fourier transform from the basics. That is, we started with the Fourier series, and I told you that for a periodic function fx for a period t, a function can be uh, written in the linear combinations of sines and cosines in this form. That is, fx can be written as a naught plus summation n equals to 1 to infinity an cos 2 pi nx upon t plus dn sin 2 pi nx upon t. A naught, an, and bn are called as Fourier coefficients, which are given by the following integrals as listed below. And then I try to write my sines and cosines in terms of linear combinations of complex exponentials, and eventually we ended up getting that your function, which is fx, which is periodic with period t, which can at most accommodate finite number of discontinuities in one period, can be written as linear combinations of some complex exponentials. And here cn's are some constants. Okay, and then we actually try to see that what happens if we make a period of a function as large as possible. So what happens is, even a periodic function, a periodic function tends to become an aperiodic function, or in other words, you can see that an aperiodic function is nothing but an infinite limiting representation of a periodic function itself. So on those lines, we tried to develop theory for the Fourier transforms, and eventually we ended up saying that if my function fx is a continuous function which can have at most finite number of discontinuities. It can also be a discontinuous function. I'm saying it means that if my function fx is a function which can at most bear a finite number of discontinuities in one period, the Fourier representation of such function is given by 1 upon root 2 pi minus infinite to infinite f of x e to power minus iota kx. And the inverse Fourier transform for the same is given by 1 upon root 2 pi gk e to power iota kx dk. And here you can say that both of these, like fx and gk, are Fourier transforms of each other. Okay, and then we actually went on to write this thing, that if function f of x possesses no more than finite number of discontinuities, and if this particular function f of x is absolutely integrable. Okay, absolutely integrable means the value of minus infinity to infinity modulus of fx dx is less than infinity, then I can say that my function has a Fourier transform. Also understand that Fourier series is valid only for the periodic functions, and here your any periodic function can whose Fourier representation is to be written can be written in terms of written in terms of the linear combination of various frequencies. But such representation again, you can have only discrete set of frequencies here. Rather, when you want to write a function's Fourier transform, here you can use all the frequencies of such kind by varying x. You can have all sort of continuous range of frequency because you're integrating it from minus infinity to plus infinity. Now your function can be written in terms of like Fourier transform of function. You can say that the Fourier transform of function would tell us what sort of functions, you can say what sort of functions, like sinusoidal functions only I'm referring to, of what frequencies or what amplitude should be superimposed to get the original aperiodic functions. Okay, the only difference is that you can say that whereas a Fourier series would demand discrete frequencies to generate a periodic function, in the case of Fourier transform, we only require continuous range of frequencies to generate an aperiodic function in general. Okay. Further, I went on to also say that understand that this Fourier transform is after all a mathematical construct. Okay, but for example, when you use it for certain physical applications, so one may be tempted to ask, what is the dimension of k? So always remember, the dimension of k is inverse of the dimension of x. So for example, if the x, that is the variable of integral x, it represents your length. Okay, say for example we want to find Fourier transform of some function in time domain. So basically x would then represent time. So your k, that is k here, which is the argument of the Fourier transform, has the dimension inverse of the argument of x, inverse of the dimensions of x. So I hope till now everything has been you might have got. Now let us start with the first case that we actually were doing. So if you remember, the first thing that uh, I was actually telling you in when it comes to the periodic function was a square pulse. So basically, what I'm going to do is the first thing that I'm going to choose is that I'm going to find the Fourier transform of a single square pulse. So let us start with this. Single square. So we are going to find what is the Fourier transform of a single square pulse. Okay. So for example, the first thing that one needs to understand is what is that single square pulse. So basically, single square pulse can represent an impulsive kind of thing, impulsive force. It can represent impulsive force, or you can say sudden surge of current or something of that sort. Okay. Uh, you can say certain surge of current or some quantity like this, which is non-repetitive in nature. That is, it actually upsurged at some particular time, instant of time, and then it was all zero. Okay. So for example, um, if I say that, let us see, this is my square pulse. So let me represent the square pulse in this form. So from the instant of time from -1 to +1, let's say the unit is 1, and otherwise the unit is 0. So basically it represents a square pulse, a finite square pulse here. So this represents, okay, and one needs to see whether it satisfies the property. The first property that was there was -infinite to +infinite fx mod dx must be finite. So if you integrate -infinity to +infinity, your function is your function is such that it is 1 from -1 to +1. So it will be like -1 to +1, it is 1, and all otherwise it is 0. So I'll write 0 here because otherwise it is 0, so forget about all those things. So eventually you get answer as 2. Clearly it is less than infinity, that is the integral is absolutely finite. कोई दिक्कत नहीं. So I can say that my integral fx is absolutely convergent from -infinite to +infinite. So integral of fx is absolutely convergent from -infinite to +infinite. This is quite clear. Secondly, this particular function only has two discontinuities. Rather, it is not periodic as such, but it is suffering discontinuities at 2 points. Okay. Now this also leads me to one more thing. Okay. So I have told you that your whenever I was talking about the Fourier transform of a function f of x, then I was saying that the function can have at most finite number of discontinuities. Okay. Now the question arises that overall I can write my function in form of a like you can say that Fourier integral can be written. But what about discontinuities? What about discontinuities? So what is the value of the function at such discontinuous points? So for that, always remember I'm writing it without proof only. So let fx be a, I can say, a sectionally continuous function or a piecewise continuous functions on interval, let's say from minus infinite to plus infinite. Okay, and let's say it is absolutely integrable also, that is it satisfies the criteria for existence of the Fourier integral. It is absolutely integrable also. Then the Fourier integral, then the Fourier integral of fx converges at each point of continuity. This is fine, each point of continuity. Now question arises at the point of discontinuity, at the point of, let's say in this particular case, x equal to plus 1. So if you go towards 1 minus, your function is 1, and if you go towards 1 plus, there is 0. If you go towards minus 1 minus, it is 0, and if you go towards minus 1 plus, it is plus 1. So basically x equal to plus minus 1 are the points of discontinuities. So what about function on these points? So I'm writing it without proof right now. I'm not going to prove it. Okay, but just remember, at the point of discontinuity, at the point of discontinuity, the Fourier integral converges to the averaged value. Let's say I'm I'm saying that the point of discontinuity is, let's say, fx. Then the Fourier integral would converge towards what? It will converge towards f of x plus f of x minus divided by 2. Okay, so where f of x plus is simply the limit to the right hand side of the function, and what is fx minus? It is limit of the function to the left hand side. I hope it is clear till now. So if anybody has got any doubt, please you can have you can you can write it on comment box. If it is like, you have to understand कि हम लोग क्या कह रहे थे कि जब भी हम Fourier transform define करने की कोशिश कर रहे थे, we were saying that we are defining the Fourier transform f of x. F of x can be piecewise continuous function, so it is bound to have some sort of discontinuities. What about the value of the function at discontinuities? So the value of the function, or you can say the Fourier integral at the point of discontinuities, is nothing but it is equal to the limiting value of function towards the right plus limiting value of the function towards the left divided by 2. Is that clear? Okay, so I hope there is no doubt as such now. So what I'll see. Uh, So I know that my functions, you can say that this particular square pulse basically satisfies both the condition. That is, one, that my function is absolutely integrable from minus infinite to plus infinite, and secondly, it is only bearing two discontinuities here. However, this is not a periodic function in general, but otherwise it is a piecewise continuous function only. So it satisfies both the property for existence for the Fourier integral. Then if I have to find uh, if I have to find what is the, you can say, what is the Fourier transform. What is the Fourier transform of the given function? So what would be the Fourier transform? Whether you write f tilde k or you can use gk as used by the initial lecture, it will be minus infinite to plus infinite. I can write f of x e की power minus iota kx dx, and then I think 1 upon root 2 pi also would follow. So gk would simply be equals to what? It will be equals to 1 upon root 2 pi from minus 1 to plus 1, and this is e की power minus iota kx dx, which is simply equals to what? Which is simply equals to gk 1 upon root over pi, and this will be minus 1 to plus 1. Okay. Now, if you place the limits, then you are going to get what? So you can clearly see that your gk is simply, it is equal to 1 upon, this is, if you take negative common, so what I'll get? Iota k. Okay, so what I'll do, I'll multiply by 2, I'll multiply by 2 here. Okay, so I'll multiply it by 2 both sides, and then what I'll get, so it's quite easy to see that gk would be equals to what? Gk will be equals to, um, okay, I know that this is, so I'll write it here, e की power iota theta minus e की power minus iota theta divided by 2 iota is simply what? It is equals to sine theta. So I'll simply write here, it will be like root over 2, sorry, root over 2 upon pi, and then I can write, it will be simply sine k divided by k. If you see, this would be the case, because see, e की power iota k minus e की power minus 2 iota k would be equals to, I think this would be equals to this only. This would be sine k upon k. I hope it is clear. Okay, and if you want to make the graph for the same, so you can say that as k tends to infinity, it will go towards 0. So as k tends to infinity, this particular Fourier transform would go towards 0. But you see, it is multiplied with sine k as well. With sine k as well. So if you want to, let's say this was 1 upon k, or this was 1 upon x here. Okay, so what will happen? Your function would initially, this is 1 upon x, how it behaves, this is 1 upon x, and if sine is somehow like you can say enveloped in this, so how the graph would behave this way. So what will happen, initially as x tends to 0, your 1 upon x would dominate. Okay, so as x tends to 0, your 1 upon x would dominate. However, sin x would not leave its character, so it is going to create some sort of oscillation. So how the graph is, I'm just tentatively making the graph. So as x tends to 0, this is going to be very large, and then x tends to infinity, what will happen? It will go no doubt initially like this, and then it will try to die. And this is how you make the sort of, you can represent your the Fourier transform of a single square pulse. So this is how you draw the graph of Fourier transform is the Fourier transform of a single square pulse. I hope it is clear. Okay. Now you see, there were important integrals which are called as Dirichlet integrals. There is an important integral which is called as the Dirichlet integral, and we are interested in this. And the integral is, we want to find how would 0 to infinity sine k dk upon k, what will be the value of this particular integral. Okay, what will be the value of this particular integral? And I will use the Fourier transform. By the use of Fourier transform, I'm going to find this integral. I'm going to find the integral. So by the use of the Fourier transform, I'm going to find the integral. See, I knew that if I am going to take the Fourier transform of the square pulse, the single square pulse from x equal to -1 to +1 if it is 1, the Fourier transform, so this is your x space, x versus y, and here it is your k space. So if I take a Fourier transform here, so what is happening? Your function becomes this. Okay, so this is how your function will become. That is, your Fourier transform is given by root over 2 upon pi, and then you have the sine k. Okay. I hope it is clear. Okay, now I want to find this integral sine k upon k. Okay, from 0 to infinite. So what is one thing that I can do? I can try to find the inverse Fourier transform. So what I should do? We will try to find the inverse Fourier transform. So we'll try to find the inverse Fourier transform. I know that inverse Fourier transform for this particular function will yield me this particular thing, that is, it from -1 to +1 it will be equals to 1. That is one thing. And secondly, while I am doing an inverse Fourier transform, I'll integrate this sine k upon k, and indirectly I'll be able to understand what is the value of this particular integral sine k upon k. I would recommend that I have already done the integral in the complex integrals also for the same. You can see the same, but I'm trying to use the Fourier transform to find the integral sine k upon k from 0 to infinity. So that is one thing that you can see the beauty of the Fourier transform. So what I'll do, I know what is my function f of x. So function of f of x, I can write it as 1 upon root 2 pi from -infinite to +infinite. It will be the fk, which is equals to root over 2 upon pi, and then I have simply sine k upon k, and then I have e to the power iota kx, and I can write dk. And now if you see 2 gets cancelled, so simply your function f of x, I can write it as 1 upon pi from -infinite to +infinite. I can write sine of k divided by k, and see e to the power iota kx, I can write as cos kx plus iota sine kx dk. Okay, now you see on any day you can see that is sine k upon k. This particular function is an even function. So if it gets multiplied with again sine kx being odd, so overall this multiplied by this will be an odd function, and limits are from -infinity to infinity. So forget about this. This will be 0. This particular integral would give you 0. So eventually, I can say that my f of x would, after all, be equals to what? F of x would simply be equals to 1 upon 2 pi, or rather, I can say 2 upon pi from 0 to infinite. I will write sine k upon k cos kx dk. Sorry. and I know what is my function eventually. So if I'm taking the inverse Fourier transform for this particular function, I will get back this particular function, which is nothing but it is equals to what? It is equals to this particular function is equal to what? It is equal to 1 if mod of x is less than 1, and if mod of x is greater than 1, then it is simply 0. Or in other words, I would write that integration from 0 to infinity sine k cos kx dk upon k is simply equals to what? It is simply equals to pi upon 2 if mod of x is less than 1. Simply take it all over there. It is equal to 0 if mod of x is greater than 1. And what we want to find what is the integral sine k upon k. So so what do you understand what kind of integration is this? This is an integration which will depend upon x only. So this is an integration but only would depend upon x, because see, after all these this is an integration over k. Your limits will be placed at k, so you will be left with x. So in particular, if I want to place x equal to 0, the integration would reduce to 0 to infinity. It will be simply sine k upon k. Nothing would get affected on the health of the right hand side, because uh, for we want to find it for x equal to 0. So basically it is equals to what? It is equals to pi over 2, because x equal to 0 would fall in this kind of definition. So this is an integral. And this is what we actually do from the complex integrals also. This is sometimes referred to as the Dirichlet integral. So the Dirichlet integral from the Fourier transform also, I have evaluated that this particular integral is equals to pi upon 2. So understand this particular fact. So basically what I have done today, I have tried to use the Fourier transform theory that we developed yesterday. I gave you one more thing, that if f of x is piecewise continuous from minus infinite to infinite, the Fourier integral of fx would converge to each of the point of continuity. But what about the point of discontinuity? The Fourier integral would converge to these discontinuity points also, and the it will converge to what? It will converge to the f of x plus f of x minus divided by 2. That is, if x is the point of discontinuity, all you need to do is you just see on the right, just see on the left, whatever is the value of the function divided by 2. So for instance, so this was the case, sine k upon k, and it was the case for what? It was, you can say that this is for at x equal to 0. You found that at x equal to 0, simply this case would be valid. So I have simply written as pi by 2. And you can see that here also, this particular integral, I'll say this as ix now. So here I as a function of x is given by 0 to infinite sine k upon k cos kx dk. This integral is clearly discontinuous at x equal to plus minus 1. It's clearly discontinuous at x equal to plus minus of 1. So one has to see how to find. So I know that from 0 to infinity sine k upon k dk is simply pi by 2. Okay, this is simply pi by 2. Is that clear or not clear? Now, if I'm saying that this particular integral, that is sine k upon k cos kx dk, I want to find this particular integral. After all, what is this? This is after all a Fourier integral, isn't it? It is after all a Fourier integral. So I will use the property that I stated very early today, and the property was that whenever your function suffers a discontinuity, whenever a function has a discontinuity, the Fourier integral, or its Fourier integral, I would say, or its Fourier transform, I would say Fourier integral, at that particular point of discontinuity, I'm saying at that particular point of discontinuity equals to the average value of the left hand limit and the right hand limit of the function Okay, so basically, if I want to evaluate this particular integral, that is Ix, if I want to evaluate from minus infinity to plus infinity sine k upon k cos kx kx dx, this integral I know it is pi by 2 at mod x less than 1, and at mod x greater than 1 it is equal to 0. So what about x equal to plus minus of 1? It will be equals to pi by 2 plus 0 upon 2, that is pi by 4. So I can write my I of x, which is given by this integral, is simply equals to pi by 2. If mod of x is less than 1, it is equals to pi by 4 by the continuity by finding the average value to the left and average value at x equal to plus minus 1, you can find pi by 2, and for mod x greater than 1 this value would be equal to what? 0. Now we want to find next we want to find some Fourier transforms. Next we want to find some Fourier transform. Let's say I'll take an example and then we'll do it. So let us take example of I'm just using the context. I'm not explaining you the context, but I would just use the context. I mean, I'm going to use the you can say what I could say. I would say that I would just use the function. So don't stick it. So let us take the Fourier transform of the electric field in the radiated wave. So I'm going to use it basically, or you can say, if you don't want to look like this, you see like this, you can also say that uh, uh, I'm just considering a function. So most of you have done damped harmonic oscillation. So considering a function which represents displacement of a damped harmonic oscillator. Okay, damped harmonic oscillator. Okay, so I know that the damped harmonic oscillator. So for all, let's say for all time less than 0, it would hardly mean anything. So I'll write 0, and for all t greater than 0, it will be some function which is whose amplitude is exponentially decaying. Okay, this is the function, and we want to find the Fourier transform for this particular function. Or otherwise, this particular equation represents where you can take as a displacement of the damped harmonic oscillator also, or you can say that it also represents the electric field in the radiated wave also. So in any case, this is a function which is given to you, and I want to find you can say what is the Fourier transform of this particular function. So if I want to find the Fourier transform of this particular function, so g of omega instead of k, because here I'm just writing seeing this omega naught, I'm using omega, it will be equals to 1 upon root over 2 pi integration from minus infinite to plus infinite. Instead of iota kx, I will write minus iota omega t, and this is e to the power minus t upon capital T, and then I have this sine omega t dt. Okay, and if you want to see, if you want to convert this sign, if I convert this sign in form of exponential, so I can write exponential iota omega naught t minus e to the power minus iota omega naught t divided by 2 iota. So if you do this, this is all going to be some exponential stuff only. So I'm directly writing the answer. This is quite easy for you to see that this will be equal to what? 1 upon root 2 pi omega 1 upon 2, and this is 1 upon omega plus omega naught minus iota upon t, and then there would be minus 1 upon omega minus omega naught sorry minus iota upon t. This is how your g omega would be. uh, you can define your g omega in this sense. Like if you integrate this up from minus infinity to plus infinity, you will get this. Now you see, so if your ft What was Ft? I told you that let's say Ft represents, electric field in the radiated wave. Electric field in the, okay. So let's say Ft represents your radiated electric field in the uh, you can say radiated wave. Okay. Uh, you if you go through the theories of antenna, uh, one direct thing I'm right now stating, that the radiated power is proportional to Ft ka mod ka square, and the net radiated power is given by the integral of Ft ka mod whole square, is given by the integration from 0 to infinity Ft ka mod ka whole square dt. Okay, so this is something that I'm you can say sorry, this radiated energy will say, because radiated power is proportional to this. If you multiply this with time, then you will get power is proportional to Ft mod ka square, and if you multiply it with time and integrate it, you will get energy radiated. You'll get energy radiated. In terms of if you want to write in terms of frequency, then g omega ka square mod ka square would then represent your energy radiated. It would have been energy radiated if I would have integrated over frequency. Now I have not integrated it, so g omega ka square would represent energy radiated per unit frequency interval. Obviously, some constant also would come, but just giving you an idea of it. Don't worry if you are not getting it. This is from the uh, like in antenna theories of current in antenna or something. But just try to understand that uh, antenna radiated per unit frequency interval. Because had I multiplied it with 2 omega and integrated it, it would have given me energy radiated. So basically, what would be g omega ka mod ka square? It would be energy radiated per unit frequency interval. Now one can see that as omega tends to omega naught, clearly the second term will dominate. You see, as omega tends to omega naught, this term would go to very large value because it is going towards zero, and overall it will go towards very large value. Or you can say that the second term would dominate. Because you see any case, and let's say if I'm talking when I'm taking t very large. So if I take t very large, you can see that my g omega, which is my this Fourier transform g omega, the second term would dominate. This second term would dominate. Okay, and when I say this second term would dominate, so I will write my g omega could be approximately written as minus 1 upon 2, 1 upon omega minus omega naught minus iota upon t. This is close to omega naught, I'm saying. This is close to omega naught, I'm saying. And if I want to say what would be g omega a mod, I can say that this will be equal to simply g omega a mod will be simply 1 upon 2, 1 upon omega minus omega naught ka square plus 1 upon t ka whole square ka root over also. And then uh, this is one thing. Okay. And if I want to plot it, so how the plot would look like, I'm just trying to show you. See, as omega tends to infinity, it will go towards 0. As omega tends to minus infinity, again it will go to 0. There would be a certain peak or there would be a certain surge at omega equals to omega naught. So it will look like sort of Gaussian kind of thing about omega naught. So this is simply your g omega ka mod ka square versus omega. Now if your g omega is scaled down by a factor of 1 upon root 2, so clearly your g omega ka mod ka square would be halved, because and when it is halved, basically when it is halved, this particular width, this particular width is called as half power maximum. This width, particular width, this is I would say that this particular width, gamma at half power maximum. And so basically, what are those points where it will be halved? That one needs to see. That one needs to see. Okay, that one needs to see. So basically, you can see that when omega is equal to omega naught plus minus 1 upon t, when omega is written as omega naught plus 1 upon t, so basically your g omega would be what? I'm just expressing the approximate value, 1 upon 2. It will be simply 1 upon, this is omega minus omega naught. So omega minus omega naught would be, if I take plus sign first, it will be 1 upon t minus iota upon t. So this is what I'm doing at, let's say, I'll divide it into two sections. That is, omega 1 is simply omega naught plus 1 upon t, and omega 2 is simply omega naught minus 1 upon t. So if I do these things, what I'll get, this is at omega 1. So at these values, I'm trying to find what is g omega 1. So g omega 1 would simply be equals to what? It will be, and if I take a mod of it, so it will be, I think, 1 upon 2, and it is be 1 minus iota ka mod. Okay, and obviously there would be t as well. So t is here. And what would be this mod? This mod will be, I think, 1 upon root over 2. It will be 1 upon root over 2 t upon simply 2. This is g omega 1 ka mod. And what is g omega naught? G omega naught is simply t upon 2. So you can see that at this particular omega 1, that is omega naught plus 1 by t, your g omega is scaled 1 upon root 2 times g omega naught. Or in other words, at these frequency, your g omega square would be halved. So basically, this would be your omega 1, and this would be your omega 2. What is your omega 1? Your omega 1 would be omega naught plus 1 by t, and your omega 2 would be omega naught minus 1 by t. And what is this width then? This width would be the difference of omega 2 and omega 1, which will be equals to what? Which will be equals to 2 upon t. Okay, in terms in physics, if this, let's say this is your frequency, let's say this represents your frequency. What does that represent? It would represent, in terms of, let's say, Heisenberg uncertainty principle. I will also come to this later on, but just giving you an insight. What does this represent? This would represent some measure of uncertainty in energy. So basically, what happens is, if you want to represent your particle, a Gaussian wave packet is preferred, and the width of this particular Gaussian wave packet would would, would would actually imply some measure of uncertainty in energy, because energy is what, h ket omega now. So basically, it will represent some measure of uncertainty, and one of the forms of your Heisenberg principle of uncertainty expression gives you delta into this will come on later, but just giving you an insight. Delta into delta t is given by almost equivalent to h ket, and from here you know that your uncertainty in the energy, uncertainty in the energy is inversely proportional to delta t, which happens to be the width, which happens to be the width. Okay, so one can see that uncertainty in the time period is inversely proportional to delta e, because delta e is this. So I can write that that if you try to resemble it with, I'll come to this on later on also. If you're not following it, I'll come to all these things later on. If I want to resemble it with the Heisenberg principle of uncertainty, relating the energy state with the time period of that energy state, relating energy of a state with its time period, one can say that this time period t is inversely proportional to the width, which is gamma, which I've written here. You can see that this gamma is inverse is what it is equals to 2.8. So basically, it is inversely proportional to what? T. And what is this gamma? Gamma is this. You can say that half-width full maximum. This particular gamma is what? It represents the uncertainty in the energy. So it's inversely proportional to gamma, which is the measure of uncertainty. This is the measure of uncertainty in energy or frequency. So I know this is quite difficult for you to follow right now. We'll come to this later on, but please keep things in mind, because actually this is from sort of, you can say that this is something that you don't know right now. You do not know about the physical context of the same. I've just given you some directions where you can just think over it, that if Ft represents the electric field in the radiated wave, you just think about Ft ka mod ka square. Even if you cannot think, just think about the dimensions and you will be able to get what I'm trying. So radiated power will be directly proportional to Ft ka mod ka square. And if I want to find and if it is time domain, then Ft ka mod ka square dt would give you the radiated energy. And if I want to write again this time domain into frequency domain, g omega ka mod whole square would give you energy radiated per unit frequency interval. Now what I have done, I have tried to plot this particular g omega around omega equals to omega naught, and you can see that it will be peaked at omega naught. And instead, if I'm not draw this particular thing, if I draw g mod ka whole square, because this is containing an iota term, so if I plot g mod ka whole square, sorry, that's a square. I'm not taking a square. Okay, if I take this, I'll get a root over. I'll get rid of root over if I do a square all over. So overall, this 1/2 omega minus omega naught ka square plus 1/t square. If you evaluate at omega equal to omega naught, you will simply get t. If you evaluate at omega is equal to omega naught plus minus 1/t, you see here. So you can see that at these particular points, your g omega would be scaled by a factor of 1/√2. And if g omega is scaled by a factor of 1/√2, then obviously g omega ka mod ka whole square would be halved. So basically, these omega 1 and omega 2 are those 2 points where a g omega ka mod ka square would be halved. See, energy is represented by h ket omega. And if you just have certain idea of Heisenberg principle of uncertainty, if I just want to explain you that a Gaussian wave packet is a description of, you can say, a particle. A Gaussian wave packet would idealize your particle, and this particular you can say width would give you an idea of what amount of uncertainty this carries in terms of energy. Okay, so basically this would give you I'll just come to this point lately with greater detail, but just understand one of the expressions of your Heisenberg principle of uncertainty states that delta into delta t is almost equal to h of ket. It relates the energy of the particle, or energy of a state, and the time period of that particular state. Okay, energy of state and time period of that particular state. And if I know, if you can clearly see that what is delta E, uh, it represents what? It represents the this particular width, and this is equal to 2/t. So you can clearly see that the uncertainty in energy is inversely proportional uncertainty in the energy of a state is inversely proportional to the time period of that particular state. Okay, so I hope I have been able to give you just some physical insight. Although in this particular lecture series, we are going to uh, moreover see how to do things at first, and then as we go along in physics, we are going to see much of these applications. I hope I've been able to explain you. If you're not getting anything, if you have any doubt in any of these sections, please let me know through your comments. Till then, take care.